everybody. We hope you have enjoyed your lunch. And so I'd just like to introduce John Britton from GitHub that will let us discover some of the internals of Git. Thank you.
Thank you very much. So hi everybody, thanks for coming. I'm going to be talking about the internals of Git, how things work. But before we get started, I want to mention two things. One is I took a lot of inspiration for this talk from one of my colleagues, Matthew McCullough, so he deserves credit for a lot of this. And also, I want to just ask, how many of you use Git already? Okay, everybody, almost. How many of you know how Git works inside? Not that many. Okay, good. So some of you might have already heard some of this before, but hopefully it's new for most of you. So Git is a command line tool. It's for version control, and it has a bunch of different components. It looks like this. There's probably 50, 80 commands here, and it follows the Unix principle of doing one thing and being composable. All right. So each command just does exactly one thing, and they work together to accomplish the end goal of revision control. So the commands you're used to, like git add, git commit, git merge, under the hood, those are all doing multiple steps, and we're going to kind of walk through some of those steps. Another thing to be aware of when you're working with a Git repository, people often think about like your history, right? Git is your history. It's got all the revisions of my code. I can go back in time. But sometimes people don't understand this whole staging and working area. Well, the working area of your code is like the working directory on your machine, and I think you're all pretty familiar with that. You use your editor, Emacs, Vim, whatever you use, and you edit your code. And then you have this kind of interstitial stage area where you can actually kind of pre-select parts of your code to be committed or not to be committed, and that's the staging area. And you can also think of the staging area as like a proposed commit. This is the stuff that I'm about to turn into a commit, and when you say commit, that's what will get written. So let's take a look at that. So I have my terminal here. I'm just going to make a new directory called example, and I'm going to do git init. That creates a new Git repository for me. So what happened here? If I look at the directory, it looks like I made, .git, cd example, git init in our project. And if I look inside, there's not really anything there, but there's a .git directory. So when you run git init, it just creates this directory, and everything with Git is done on the file system. There's no special back-end process. There's nothing going on. It's just all on the file system. So if we look into the .git directory and we do, say for example, tree, you'll see a bunch of stuff. You see this head, config, hooks, and then of particular interest to us is the objects directory and the refs directory, and we're going to dig into these more in a little bit. But I kind of wanted to show the staging area. So for example, say I touch foo. I make a new file. I'm in my project, touch foo. You can see git status shows that I have an untracked file. And now this is where the staging area is used. You say git add, foo, git status, and you can see that there's a change waiting to be committed. Now if we look back into that .git directory, so tree.git, and I'll show you the objects directory. Before this was empty, and now we have a new object written into the objects directory under this E6 subdirectory. I'll get more into that in a little bit. But then if I go back and I say git status, I can do git reset foo, and status goes back to an untracked file. So this is like how you manipulate the staging area and what happens under the hood when you in the .git directory. So everything in Git is based around hashes. So you might be familiar with if you've used other version control systems before Git, something like Subversion, you have sequential version numbers. One of the reasons you can't do that is because if you use a distributed version control system, how do you decide who gets revision n+1? So say we both copy the code from the server at revision 10, and we both make commits. How do we find out who gets revision 11 and who gets revision 12 without talking to the server. So Git uses hashes for revision identifiers. It uses SHA-1 hash to be exact, and SHA-1 is like a fingerprint. Essentially, it takes some content, it runs it through this function, and it comes out with a fingerprint. And that fingerprint is 40 hex characters, and it looks like that. Now, I'm sure some of you are already asking, if you're sophisticated, you know that hashes can collide, and you're saying, what does Git do if hashes collide? Well, the chances of that happening are like slim to none. But if you really want to entertain the possibility of that happening, what happens is under the hood, if an object has the same fingerprint as another object, one of them came first. So say, let's use a simple example. If the empty string and the string hello world happen to have a hash collision on of their contents, what would happen? Well, depending on which file you committed to your repository first, that's what would stick around. Because Git uses these hashes as like a unique identifier so that it knows when to do performance optimizations, like should I write this file to disk? Should I transfer it over the network? So it's always based off of this hash. So let's jump back. So we saw in our .git directory, tree.git objects, we saw this E6, 9DE, 29, etc. What I did before is I did touch foo, and then I did git add foo, right? And what does that do? Well, it looks at that file foo, and it looks at its contents, and only the contents. It doesn't care about the name of the file when I do this. So for example, if I touch another file, and I do git add another file, you might expect another object to show up in the objects directory, but that won't happen because .git objects, both of those objects are empty files, and the hash of an empty file is always E6, 9DE, whatever. You might think, for example, well, if I do print f empty string piped to git hash object, right? If I say send an empty string to this hash object plumbing function, what should I get out? There it is. You have E6, whatever. And if you don't trust Git, if you want to just take a look at it and say, okay, well, can I do this without using Git at all? So we could say printf empty string pipe to SHA sum, which is just a binary I have in my path. And that's different. Why is that different? Well, under the hood, when Git writes this empty file, or actually any file, it writes out a little bit more information. So I'll just hop over here real quick. So I have... here's my, yeah, all right, there it is. So it's blob, and then the number of bytes in the file. In our case, it would be 0, followed by the null byte, and there you go. So what this leads to is when you have a file stored in the Git objects directory, if it's an empty file, it will always have this hash. But if it's a different kind of empty object, say for example, an empty directory, it would be, we could say something like this, tree. I don't know if this is exactly how it works, but the empty tree is always 4682, and as some of you probably already know, Git doesn't support empty trees. It just kind of says, we don't care about empty trees. So let's take another example. Let's open up, do this. Git status. We can see that we have one change ready to be committed and one that's not. So this is kind of that working area where we can, pick and choose what we're about to commit. And I can say git add foo. So now I've selected both of these empty files to be added to my repository. And when I create a commit, git commit add some empty files. Now if you take a guess at what might happen here, something happens in the objects directory. So tree.git objects. You can see we have two new objects. Well, we created a commit, right? So we know that this E6 whatever is the empty file, and we have two empty files in our revision history right now, but they're both pointed to on the same object on disk, because why store the empty file twice, right? But then we created these two new objects, and one of them we can see up here 0A246 or 246AB is right here. So that's the commit that we just created. But what's this other object? Git cat file-t, and I'll say 0a246, and you can see there's the commit that we just did, and we can say -t e6-9de. Okay, there's a blob. So what's this other thing that we have there? 6a-cdd. It's a tree. So every time you make a commit in Git, we're creating a new object in our objects there that references a tree, right? And if we go a little further and we take out like a pretty output of what that tree looks like, we can see that it has 2 entries. And if it was a little bit smaller, it would fit on the right lines, okay? And each line of this tree is just a simple text file. It shows the file 100 is like it's a regular file, it's a blob. 644 is the permissions on disk. Blob is the type of Git object that we have, and then we have the hash. And both of these have the same hash. There we go. So in a traditional SCM like Subversion or others, they use delta storage. They use, store the differences. Only these lines of file A changed. Only these lines of file B changed. Let's just store that. And it sounds like it's more efficient. In Git, we do actually a copy of the entire tree. So from commit to commit, we have what's called directed acyclic graph, and it looks something like this. A linked list is this points to this, points to this, points to this. In this case, there are no cycles, so there are no loops in our graph, and it's something like copying an entire directory. So every time you make a commit, you can think of it as copying your entire project and just making another one. And you know how in like math class or science class, the teacher lies to you about negative numbers, or they don't tell you something is really happening under the hood? I'm not going to do that to you. So what really happens in Git is that each time you make a commit, a new one of these commit objects is written to the object's dir, and it references back to those old hashes. So if a file didn't change, we made a new commit because something in our whole revision history changed. But if a given file didn't change, we just reference that same hash. So if we look here, like if I make a touch, or if I like nano hello world text hello world, and I do git add hello world.text, git commit -m hello, right? Now if I look at that commit object, git cat file, and then I'll grab the hash there, we can see, okay, we have that commit, and we see the commit message, and we can see that it points to a tree. So we've kind of already talked about the fact that there's a tree and it points to blobs or other stuff. So we can grab this hash, and I can say git cat file -p and that hash. So that's going to show me what's inside that tree. And now you can see it's exactly the same first 2 lines as we had before, pointing to the same empty hash, or like the hash of the empty file that's on disk for another file in foo. And then hello world points to this new hash, which, if we want to try it out, we can say git hash object hello world.text, and you can see that it matches the hash that's in that tree object. So essentially what's happening is we're hard linking to each, back to other versions of this file that already exists on disk every time we make a new commit or make a change in our repository. Another thing that you might think about is, how about let's take a look inside of that file. So if we say tree.git objects, right, and we see all these objects that we have. What if I cat out .git objects E6-9de. What do we expect to get out of this? Well, you might think you'll get an empty string, but then we realize that even though it's an empty file, Git stores that it's a blob and it has 0 bytes. So we would expect that to come out, but what comes out is garbage. It's zlib compressed when it's written to disk. So we can do something like, if we go here, actually I have it already, which deflate. Okay, so I have this command aliased to deflate. It's just a Perl mcompress. This is just so that I'm not using Git to do it. You can use any zlib library. There's a homebrew formula in like the dupes keg that you can add for zlib. But deflate.git objects e6 whatever, right? And you can see that it says blob 0 bytes All right, and then we can do Git also has an internal command, plumbing command that's git show, and then you just give it a hash. So for example, E6 90E29, and it's nothing. But if we did that with, for example, this hello world, so let's see, where is that stored? Git hash object hello world. So we have this 9f whatever. Grab that and I can say deflate.git objects 9f, and it will show me it's a blob, 13 bytes. It says hello world carriage return, and git show that, and it will show me. So under the hood, this is what Git's doing. It's writing all this stuff to disk, and you can kind of see where it's storing everything. So each of those files, since it's only stored once and we hard link to it, it's still compressed. So this is one of the reasons why when I said, you might think that storing diffs between commits is more efficient. Actually, this works out to be a lot more efficient, especially when you introduce the concept of a pack file. So when you clone a repository from GitHub or from another person, it doesn't transfer all these objects individually. It actually pulls them together into pack files, which are a zlib compressed also. So it's kind of like the whole repository can be compressed over time. So far we've talked about about blobs mostly. We talked a little bit about trees and kind of mentioned commits, but we haven't talked too much about what it means, what commits really are. So this is the structure of a commit in Git. I'll start from the bottom up because we started with blobs. We have this, this text called "Hello World." It's just some content, and at the very bottom of the hierarchy, there's just this object called a blob, which can be binary, can be text, can be anything. It's just Git treats it all as all the same. It's content, it's data, and it has a hash. And since every bit of content has a unique hash, we can use that as a kind of global identifier for this content. Then one level up, you have this tree, and we kind of looked inside the files. We could see that the top level tree object from our project references 3 files. 2 of them have the same hash. In this case, it references 2 blobs, and they're referenced by hashes. And then the tree itself, when we looked on the command line, if we said, for example, git show git show head dash pretty equals raw. If we take this tree, for example, so this is the latest tree, and we can do git show or git cat file dash p and give it that. We can see this is what the tree looks like, and each file in here has its own unique hash. So if any of those files change, well, what will happen? They'll have a new hash. Git doesn't move things around. It just creates a new file on disk with the new hash, and then a new tree will be created that references those new hashes. And because one little bit or one hash in the tree changed, now the hash of the new tree will have to be different as well. So this is one of the reasons why you can work in a distributed fashion. You don't have to have a central location where we can say, okay, John gets the next revision, or John gets this identifier for his tree. It's all kind of internal to the system. So then that is used to calculate the tree hash, and then you can have trees nested in subtrees. In our case, we just have one top-level tree, and then you have a commit, and the commit references a tree. Every commit references a tree, and this is what I was saying before, kind of like when I lie to you, is that it's like doing a whole copy of your entire project. Every time that you make a commit, you have a point of reference, this commit object, that references a tree. And that tree references via hard links a bunch of files on disk. So you have an exact snapshot of the entire project at any given time, but it's not actually storing, it's not like doing a CPR. It's not restoring all that data every single time. Also in the commit, you'll see that there's a parent field. So in our case, we made a commit, and that was the first commit, and the parent is nil. So this is like when you do initial commit on your repository, you're just making a commit in the middle of nowhere. Then there are two more fields, author and committer, used for who wrote the code and who added it to the repository, along with a message. And all of these pieces, combined with some date information, are used to calculate the commit hash. So what this means is that if you and I both clone the same repository, and we do exactly the same work, and we both commit at exactly the same time, we'll still end up with different commit hashes because our names are in there and things like that. If, for example, we could magically make the commit at exactly the same time, and all of our machine was set up exactly the same way, then the commit hash would be the same. And when we try to sync up with each other, we wouldn't even transfer this data over the network. It would just be like, oh, you have the same fingerprint, so we don't need to transfer it because it's the same. So yeah, that's what one commit looks like. Now, when we get into revision history and working on a project, your history looks like a linked list. Essentially, if you want to use these numbers, version 1, version 2, version 3, which I don't really recommend, but it gives us a little bit of context here. Each commit exists and it points to its parent. So if you start a new repository like in version 1, and then you make some changes, you have v2, and it points back to the commit of its parent. So you can see parent points to here, right? Now what's interesting, you can do exactly the same work and have the commit applied to your repository with a different parent, and you'll end up with a different commit hash. Everything is all part of this fingerprint. So the same thing is true for version by version. And what's cool about this is that you're basically branching all the time. There's never a point when you're not on a branch, because every time you make a new commit, you're just pointing back to where you want that commit to attach to the rest of your history. So in in version control systems like Subversion, you do a branch and it's let's copy everything, right? But in our case, what is a branch? Well, a branch isn't really a thing. It's just a pointer into our history. It just says, you've got revision 1, 2, 3, 4, 5, that we did over the past week, and master points at 5 because that's the latest thing, and we're all working on master. But you could have this other branch that's called bug 979 coming off of your history, and that's just a pointer. And the commit that you made, the commits you made on that branch were made exactly the same way as the rest of the commits in your history. So let's jump into a little bit of that stuff. So if we do this command git log, which I hope you're familiar with, it shows that we have 2 commits, right? And if we do git log -- pretty equals raw, it will show us all the underlying information that we want to know. So you can see that my first commit doesn't have a parent, but my second commit does, and that matches the one that came before it. So we could do, for example, we could open up this file, some more stuff, write it out, git status, git add hello world, git commit -m, add more stuff, and then git log -pretty equals raw. Okay, we have the same pattern, right? We have the tree, we have the parent pointer that points to here. But what actually happened? Well, if we look, you can see that I'm on master. What does it mean to be on master? Well, you run git branch, and it reports back to you, oh, you're on master. Great. Well, what happens when you're on master? When you make a commit, master follows you. And I really think it's important to think about it that way, as opposed to making a commit to master. If you're using lightweight branches, which you're probably most of you, when you're using branches, it's always lightweight. With tags, you have a little bit different situation. But when you're working on a branch, it's not that a branch is a thing. It's just a pointer into this history. So, for example, if I was to, git log and just grab this commit, and I did git checkout that commit, what does that mean? Well, it's going to be exactly the same in my on my working directory. I have that commit in my working directory. So the contents of my history, my repository at commit 514, etc., is what my working directory looks like right now. But you'll notice I'm not on Git branch. I'm not on a branch right now. It says I'm at no branch, detached head state, which sounds like I'm going to get into a lot of trouble. But it's really not that bad. All it means is that when you make a commit, you're not going to have anything to point to what you just committed. So if I touch detached head, right, and I add detached head, and I commit detached commit, right? If I do git log, I can see it there. But if I do git checkout, I'm going to grab this onto my clipboard for a second. If I do git checkout master, and I do git log, of course I don't see it on there because it's not on my history, right? Like it's not on this line of from where I am right now. It's not going back. So, but now I can't check that out conveniently. I have to know the hash. And if I look into my object store, so I can do tree.git objects, and so the hash that I copied from before of that commit was 85EC. You can see it's here. It's in my objects directory, but nothing points to it. It's just kind of sitting there. So like if we look at our slide, like imagine we're in a situation kind of like this. We've got master up at the top, and then we have down at the bottom we have just a commit hanging off and nothing pointing to it. So we could check that out. We could say git checkout that. Okay, we're detached again. We're on a point of our history graph that nothing points to, and we can say git branch attach head. Okay, and now we have a branch that points there, but you'll still notice if I run git branch, I'm still on no branch, but attached head or attach head is there. So if I do git checkout attach head log, there's my detached commit, and I can git checkout master, git log, okay, but now I can do git branch, and then git checkout attach head, git log, and it's still there. So this is just to illustrate an important point that your commits are all the commits are the same in your repository, and if you forget to make a branch before you start doing some work, it's not really a big deal because you can just go back and put the branch, move your master back and put your, a new branch on the end where you are. You had a question, yeah?
Why after creating a branch you are didn't?
So when you do git branch, and I'll show you some internals of this in a second. Git branch, what it does is it takes an argument, which is the name of a branch, and it takes another argument, which is the destination of where you want to make that branch. So for example, I could say master ~1, which would say make a new branch called name of branch, one commit before where master is. That doesn't, I'm not telling Git that I want to be there, I'm just saying make a branch there, right? If you want to do, if you want to be on the branch and make it at the same time, git checkout -b will do that for you. It'll make a branch and it will check it out at the same time so that your next commit will advance that branch.
Yeah, but
Yes.
Yes, you created a branch pointing to the revision where you were in. Mm-hmm. So you were on the branch.
So I was on it, but I didn't check it out. And when you check it out, so for example, you can have, I'll show you an example here. Git branch, branch. Here, how about this? Tilde git scripts, git graph live. This is what my repository looks like right now. I'm on this branch called attach head, which has as a parent the same thing as master. So it has that commit as a parent. If I did, for example, git branch another name, and then I run that script again, what you'll see is that I have two branches at the same spot. So you can have multiple pointers to the same commit. So this is why you're not automatically checked out onto that branch when you make a new one. And if there are questions as I'm going along, you can raise your hand and we can do it. And I'm also going to stop for questions at the end. So.
I personally found that. I mean, Eric told us this concept.
Excuse me.
Yeah, hold on one second. I think
if somebody speaks without a microphone, would you please repeat the question?
Okay, so I'll repeat your question afterwards.
Eric understands this concept of moving across one third of things. Is the way that he understood all the things. The Ref Log is your head.
Yeah, so the comment was about the Git Ref Log command being kind of a way to track where your branches have moved. So for example, if you are on master and use Git Ref Log, you can see that, the last thing you did was you added a commit which moved master forward, and you kind of have a way to track on that stuff. I might get into that towards the end if we still have time, but we'll see. So to keep going, let's see here. So we have this situation where we can have multiple branches, but what is Git doing under the hood with these branches? Like, if we look at the picture, I'll put it back to like that. If we look at the picture, you can see that these kind of gray boxes are just like saying like this is a point in our history that we're pointing to. And if we look at our our commands, we can see that here's that gray box, attach head, another name, whatever it is, pointing to a commit. But how does Git represent this internally? So tree.git, look into our Git directory. There's a directory called refs heads, and you can see inside of there that we have 3 entries. One is called master, one's called another name, and one's called attach head. And we can actually just cat out one of these files. So cat.git refs heads master, and I think you could probably guess by now what you're going to find inside. It's a hash, and that hash corresponds to the commit that master points to. So for example, if I wanted to, I could say, git rev parse, which is a really handy command. This will tell me the full hash of a given revision. So I'll say master ~2. So two commits before master give me that revision. So now I have, this is a commit hash. I can actually open up a text file, .git refs heads manual, and I'll paste that in. So I'm going to manually create a branch. And now if I do git graph live, you can see that I created a branch at my initial commit called manual just by writing some text to that file, writing a SHA-1 hash to that file. So what's really cool is that branching is basically free. You can branch all day and it's not going to cost you a dime. So it's super fast, super easy. Yeah. So let's see, what else do we want? So we just saw a little bit of this. This is about how, so if we don't have these nice revision numbers, revision 1, revision 2, revision 3, how do we kind of get around in Git? Well, we have commitish and treeish. It's basically a shortened version of the hash, and all you need to do is use the unique within this repository part of the hash, starting from the left. So you say, if you have only a few commits in your repository, you can probably get away with four characters. I think there might be a limit at 4 characters as the minimum, but essentially you don't have to type out that whole thing. You can basically reduce this down, reduce getting around in Git to a series of graph traversals. So you give a point. So for example, you could give master, which refers to a commit, or you could give a specific commit hash, or you could give a shortened commit hash, and then you can navigate from there. Since the Git underlying storage, it stores pointers to parents, so it stores pointers to the past. You can navigate in that direction. So you can say, give me the parent of this commit, or give me the parent of this branch, or give me a parent of this tag. And this little angle bracket means go back 1 parent, go back 2 parents, go back 5. You can also specify ranges with .. Give it two hashes, or master and another branch name. Basically anything that refers to a commit. Head is the most recent commit on this branch. So it's in our case, we're on attach head. So head would be, you can even see it in this output. It's 8.5 whatever. If I do git checkout master, head is now graph live. You can see that head is now here. So head moves around as you jump around in your project. And the same thing, you can go through those. Let's see here. I don't want to go through so much of that. So let's look at merging and see how that works. So if you have, for example, Git scripts, Git graph live. So say, for example, we want to merge into master. We want to merge this like attach head, which is just some random commit that we made. We can say git checkout master, which we're already on, and then git merge attach head. We could also specify a commit here. Instead of that, we could specify a commit. The side effect to specifying a commit instead of the branch is that your commit message that's auto-populated is going to show a different message, but it's essentially going to do the exact same thing. Attach head. it will ask us, in this case it's fast forward. So let's look at what that means. Git scripts. So fast forward, what just happened is that we, Git Ref Log, we merged in this attach head branch with master, which was previously down here, this 5144. And what happened was, since the two paths didn't diverge, if you can imagine, it's like, commit 1, commit 2, commit 3, and then we said make a branch and did commit 4. How is that any different from a straight line? It's not at all. So when you do a git merge on what looks to Git as a straight line, it does this thing called fast forward, where it essentially just moves your pointer from the branch you're merging into to the destination of what you're moving in. All right. The next kind of phase of doing merges is like if you have a diverging history. So git script generate random changes. This is, I don't write Python, so this is how I write Python. So I did a bunch of work. I'm on master. Git log shows a bunch of commits. This is my really awesome source code. Then I can do, for example, git checkout, or let's do this, git branch before. And I'll say this is like before I started doing that work. I didn't make the branch, but I can say master tilde 5. So let's make a branch called before at 5 before master. Okay, and I can say git checkout before. And if I ls my directory, I don't have any of that random stuff. Git checkout master ls, and there it is. So it worked. Checkout before. And now if I do, for example, touch I wish I knew Python.py. All right, git add. I wish I knew Python. Git commit. Add my wishes. All right, and now kind of contrived example, but I can show you git scripts, git graph live, and you can see that it's not big enough. I'll make it a little smaller. Okay, you can see that master is at the tip of those 5 commits that we did, and then I have this before branch that I went back in time, created the branch, and then made a commit on that branch. So you can see that I kind of diverged. Now what we want to do is we want to merge my wishes into the main line of development. So I'll quit this and check out master, and I'll make it bigger again. So I'm on master, I can do git merge before, and this time instead of doing a fast forward merge, which just kind of moved the branch pointer up, it's going to prompt me for a message, and I'll just say, yeah, whatever message. And great, it created a new commit. So if we do this git scripts graph live, you can see that we created a new commit up here, and that it has 2 parents. You can see that it has this before and this main.py work that I was doing. And you'll also notice that this before branch is still there. So we did our work, we merged it in, and now before is just hanging around. We don't really need it anymore, so we can do git branch -d before, and we don't have to worry about losing any work because it's just deleting a pointer to that commit, so the history will stay looking exactly the same. So that's that. Let's look into that latest commit. So if we do git log, we can grab this commit hash, and you notice that it's a merge commit, and we can say git show --pretty equals raw, and then give it that hash. And this is what it looks like. You can see that it's got a commit hash, and that hash is based off of all the contents that you see here, right? It points to a tree, which is the result of merging those 2 divergent points in history, and it also points to 2 parents. So these are the 2 commits that we brought together. So the underlying structure is still just this graph, and we're just pointing back to our parents, and in this case we have more than 1. There are also cases where you can have more than 2. I've never had a need for that, but it can be done. So yeah, that's how merges work. Let's see here. So somebody was asking about the ref log before, and we've got about 5 minutes left, so I'll try and touch a little bit on the ref log. So you can think about the ref log as like version control for your version control. That's how I like to think about it. It's a little bit meta. And what it does is it basically keeps track of all of the changes to your refs, to your like for example to your branches. So if I do, for example, when I'm on master, if I do git ref log, what it's going to report is a history of what I've done with this branch. So the latest thing that I did, head at 0, and this is kind of the format for specifying ref log entries. You can see that I merged in these things. The step before that was that I checked out master, and then before that I committed this thing, and I can actually go back in the ref log as well. So if I said I wanted to undo that merge, git reset -- hard head, I have to look at the ref log again, git ref log, let's see where it is, head at 1, git reset -- hard head at 1. And what this is going to do, it's going to put me back into the state before the merge, where my master branch was pointing at what it was pointing at before. So now if I do ~ git scripts git graph live, there it is. Now you'll notice that my branch that I merged in is kind of missing, though. I don't have the before branch because I didn't undo that loss. But that's essentially what you can use the ref log for. And I think I'm going to stop here and open for questions about stuff that I've covered, stuff that I haven't covered, and kind of just go with that.
Okay, thank you.
Thank you.
Questions?
What happens if there was a conflict in the merge? We get to fix the conflict, and is it just taught in the tree? What's the right way to conceptualize a conflicting merge?
Okay, so to conceptualize what happens, I kind of showed this, where'd it go? This slide before. Git operates like this. So when you say git merge, it's doing a bunch of stuff under the hood. First, it's going to grab the files that the two things that you're pointing at. So for example, I'm on master, so I'm going to merge into master. I say git merge feature X. What does it do? Well, it goes and it grabs the last representation of feature X and performs a merge. Where does it perform that merge? It does it in my working directory. So we have this concept of working, staging, and repository history. So we're working in the working directory, and Git's doing the same. If there are no problems at all, what happens is that Git stages those files, stages the merge for you, and then it commits. And it automatically gives you a commit message or prompts you for it. If the merge fails, it fails in a specific place. It doesn't fail across the whole, it might fail across the whole thing if you're editing every file on every commit. But generally it fails on a specific file, on a specific line, or a few sets of lines. So what will happen is that all of the merging that can be done will be done automatically in your working directory, and all of those merges that were successful will be staged, and the things that are unsuccessful will not be staged, and then merge will abort. It won't do the commit step. So I can show you how that looks. Let's say, for example, let's open up main1.py. Main1.py. Why is that not working? Okay, let's see. Nano hello world.txt. There we go. Okay, so let's say we have to make a branch first too. Git branch conflict. So we made a branch. We'll edit this file on the second line. Write some stuff there, and then we'll git add hello world, git commit, prepare for conflict, git checkout. Yeah, you usually don't know that you're preparing for a conflict when you do this, but it happens. Git checkout, what did I say, conflict. And now edit that same file in the same place. Let's say, for example, add some text in front. Git add hello world, git commit in front. All right, now git checkout master and git merge conflict. Now what happens here is you'll get the conflict. And if I had a bunch of other stuff happening in that branch that didn't cause conflicts, it would be staged. But if I do git status, you can look and you can see that there's a new state that you might see. This is what you see when you have conflicts. It's called both modified. It basically says that both of the references that you merged had changes that could not be automatically resolved. And it's in your working directory. It's not committed, so you can always back out of this. But you just open up the file. And then the output is essentially, this is what I had in my current working when I started, and this is what I tried to merge in. So I tried to merge in this stuff, and you just kind of pull out, the stuff that you don't want. Say, this is how I decided I wanted to resolve that, and I save it. Git status still reports that they're both modified. So you have to tell git status that I've manually resolved this conflict by doing git add, and then git commit. So what you're doing is you're manually walking through the steps Git would have done before. So I think that's a good way to conceptualize what happens in a merge conflict. And then it will still prompt you with your thing, and it will also tell you about what files were conflicted during your merge. Yeah, or I don't know how you want to select people. I saw you first.
Thanks for talk. What's so special about Git stash and Git unstash that is not available by just branching and?
So that's a really good question. There's nothing special about it at all. It's actually the same. So if we do, and I'm a little bit rusty on this, but I'll give it a shot. Let's say nano hello world. We make some changes in here, like let's stash this. Write it out. Git status. All right, it's modified. I can say git stash, and now nothing. I'm in a clean working state. This is where I was before I started editing the file. What git stash does is it says when you're in your working directory and you make changes, if you're not ready to commit them, you can kind of put them off to the side, stash them. By default, stash operates on tracked files only. So, for example, I edited a file that's already in version control. If, for example, I did, touch new file and I did git stash and then git status, it's still there because it doesn't touch untracked files. There's a command git status dash include untracked or something. I don't know exactly what it is, but you can also stash untracked files as well. But what it does is it essentially creates similar to a commit object. It just sticks it off, not attached to anything, and git stash list lets you look at them. And there's this nice shorthand notation for it. And if I grab that and I do git show that, it'll show you what it looks like. And under the hood, it's got a hash. Right? Oh, why is that not working? Git show dash dash pretty raw. Yeah, it's got my changes in there. Let's stash this. So under the hood, it looks just like a commit. By default, when you do things like Git Branch or you parse all of the revisions in your repository, you're not going to get these by default. You can actually look into this stuff and pull them out as if they were normal objects. There's Git K, and Git K accepts some arguments where you can essentially pass it all the points where you want to start traversing backwards from to show you the history. And if you use Git Revlist, what does it say? Git Revlist. Basically, it's how we talked about the tree structure. These are just kind of sitting off, not connected to anything else. There's no branch pointing to them, but the stash is. So it's just like a branch pointing to a commit. The stash points to that thing, and it's just a separate place to kind of find it. Cool. There's someone over there.
Shorter? I don't know. Throw it.
The green shirt had it first. Okay, so you can go next. Well.
Hi. So I wanted to ask, Ref Log keeps track of stuff that happens to branches, so basically to the names of commits. Mm-hmm. But when you rebase, can you back out of rebases with Ref Log? Sure. And how? Because rebase rewrites the...
So I'll give you an example. So let's just take a quick look here at our history. So we have some commits, then we have a branch that we merged, then we have another branch, and then I think we merged it as well. Yeah. So let's make another scripts, generate random changes, 5 something dot text. All right, so we did that, and then we can say git branch, another branch, master, tilde 5, git checkout, another branch, and touch feature, git add. So say, for example, in this situation, we've done something that looks like this. We have master, we branched in the past, we did some work, and then master progressed, right? And you might want to rebase this commit on top of master. So let's do that. We can say git rebase master. Okay, and now we can say that, and you can see that another branch is now rebased on top of master, but you want to undo that, right? So we can say git ref log, and we can see in the ref log that I added a feature here, and then we have this rebase stuff, right? So I'll say head at 3, git reset -- hard, head at 3. And now if I run that, I'm back to how I was. So what happened was that the ref log, and I can show you the ref log now, git ref log. Now you can see another entry in the ref log that says I reset. Let me make this bigger so you can see it. So essentially every time that I manipulated that, what was it called, another branch pointer, the ref log kept an entry. And because all of the objects that another branch pointed to are still in the objects directory, so we moved it, we had a commit, let's call it A, on another branch, and then we rebased and we have A prime. A still exists in the objects directory and will stay in the objects directory until Git purges it with garbage collection, and that happens after at least 30 days by default, plus some number of minimum objects in the objects directory, plus if you run git gc. So your ref log still has pointers to all those old commits, all those old files, all that old stuff. So all you're doing is when you run git reset hard on a pointer in the ref log, it takes you back to when that pointer pointed to those other objects. Yeah. I think we got time for a couple more.
Oh, I think one last question. So
Someone in
I
the back
take
is
it
really
from the other side of the room, just to be kind of
fair.
yeah. Oh, whose was the from back there? Back there? Okay, the farthest, the better.
First, thank you for the great talk. I used to work in the game industry where we have huge binary files like images or meshes, and one problem we had is that the idea of modifying slightly an image and then having in fact a new copy of the image in the Git repository was in fact inferior than the Delta strategy for those kind of files. I mean, it was really perfect for code, but for this kind of files where you modify a teeny bit, it just changes the binary content, and you don't have a diff strategy for those files. I'm just wondering if things moved forward for those specific use cases.
Yeah.
So I don't know. In fact.
That's a really good question, and a lot of people have that problem, especially in game development, is that you've got very large assets, and you make small changes to them, and it's just going to make your repository huge. There's not really a good solution for that in Git, and I would recommend against putting huge assets into Git. One kind of technique I've seen for avoiding that is kind of writing descriptive kind of things that generate your large assets. So for example, if you're customizing a game character, I don't know, and you can kind of write out the parameters. It's like this tall, this wide, etc. And then you can use some script to generate the binary asset, like revision control that script as opposed to the actual binary. There's also a tool, I forgot the name of it off the top of my head, but if you ask me later, I'll try and find it. It's essentially a way to externally reference binary large assets in a Git repository. What it does is you kind of specify these are the file paths that have big assets in them, and Git internally will store, a hash that points to the hash of that content. So your repository only versions the hash of the content. It doesn't actually version the content, and then you store all your big content on some separate asset server, and you can have like some kind of script that automatically pulls it down to your dev workstation. So if you have a game company and you have huge assets, you might have one main asset server, and then you have your Git repository that you can check out versions, all that stuff, and when you want to grab the assets, you just run a script, and Git has a listing of all of the appropriate assets at that time. The drawback to that is that your history is not safe forever. If you lose that, if something happens to that server, it's gone. There's no way you can kind of recover from it, but it's a trade-off.
Okay. Thank you very much again.
Thank you.
Thank you, John.
Thanks.
No problem. Thank you. Good luck.
Thank you. Oh, you're using the tree. I'm using what? Tree. Yeah.
Oh, for the lights, we don't change them during the talk because it's disturbing for the speaker. Now I will take a look.